Welcome to homework.
This is the answer to Chapter 24, problem number 73 from the Smith Organic Chemistry textbook. This problem says 4-methylpyridine reacts with benzaldehyde in the presence of base to form molecule A. We're asked to draw a stepwise mechanism for this reaction, and then we're asked if we would expect 2-methyl or 3-methylpyridine to do the same reaction and to explain why or why not. Okay, so the stepwise mechanism here is going to look like this. The hydroxide will deprotonate here. So we will get this carbon ion that is going to be the nucleophile that is going to attack the benzaldehyde. Okay, so just like this. So after that, gonna write this like this. So C6H5C. Okay, so just like this. So we'll have 3 lone pairs and a negative charge on this oxygen. That is going to be protonated by water. Okay, so then from here, another equivalent of hydroxide ion will come and grab this proton. So that'll get us to this point. Okay, and we have a lone pair and a negative charge on this carbon now. And so that will add in here. The hydroxide here leaves. And so that gets us to our product molecule here, which looks like this. Oops, forgot a hydrogen. There we go. Okay. So here's the product here. This problem calls this molecule A. So that is how molecule A is formed. Okay, and now as far as part B of this problem, so when we deprotonate 4-methylpyridine, so when we deprotonate here, the reason that this works is that we can draw resonance structures that end up placing that resulting negative charge onto the nitrogen. Nitrogen is, an electronegative atom, and so it is pretty stable to put the negative charge on there. So this is our resulting product after the deprotonation. And so we can draw a resonance structure that looks like this. Where nitrogen now has 2 lone pairs, and so it has a negative charge. And so that's good. There's other resonance structures we can draw as well, but this is really the important one. If we try to do the same thing with, for example, 2-methylpyridine, and so 2-methylpyridine would be this. Okay. There is not okay. So if we do 2-methylpyridine, we actually would expect this to work because 2-methylpyridine can do a similar delocalization. So 2-methylpyridine can go like that. And so we have a resonance structure that looks like, we have a resonance structure that looks like this. Again, where there's 2 lone pairs and a negative charge on the nitrogen. So 2-methylpyridine should work. However, 3-methylpyridine is not going to work. So 3-methylpyridine would be this. And so the point here is we're looking at the conjugate bases of these methylpyridines as acids. And so remember, the more stable the conjugate base, the stronger the acid is going to be. And so that is why we're looking at them like this. And so with 3-methylpyridine, we can draw a whole bunch of resonance structures, but there's actually no resonance structure that places the negative charge on the nitrogen. So no resonance structure puts the negative charge on nitrogen, puts negative charge on nitrogen. And so since there isn't that extra stability from doing that, 3-methylpyridine doesn't work. So 3-methyl doesn't react, and it doesn't react because those protons are not acidic enough to be picked off, and they're not acidic enough because the conjugate base is not stable enough. The 2-methyl, however, we would expect to react. So 2-methyl does react, 3-methyl does not react. Okay, and then here on the first page again is the stepwise mechanism for the reaction when we have the 4-methylpyridine, and that's the answer to chapter 24, problem number 73.